An object is 18 centimeters from the center of a spherical silvered glass Christmas tree ornament, 6 centimeters in diameter. What are the position and magnification of its image? To solve this problem, we first want to take out all the information that we have and draw a picture. So we know that 18 centimeters is the distance of the object from the center of the spherical silvered glass. So if this is the spherical object, a spherical mirror, and the object is right here, let's say, okay, so let's call this as an object, then we know that the distance from the object to the center of the spherical mirror, this is the 18 centimeters. So from the mirror to the object, it would be our DO. And from the vertex of this mirror and the center, that would be radius of the mirror. So we also know from the problem that the Christmas tree ornament has is 6 centimeters in diameter, which means we can find the radius. So first of all, let's see, this one is a convex mirror, so the radius should be negative. So let's write down the radius should be negative 6 centimeters divided by 2, which equals negative 3.00 centimeters. Now we can find the DO, which equals 18 centimeters minus the radius, which is the 3 centimeters, that equals 15 centimeters. Now what is it the problem is asking us to find is the position of the image, which is the DI, so DI, and magnification, which is our M. So I can write in my table as a question, so DI is a question mark and the magnification is a question mark. So now what do we know about the spherical mirrors? We know there is this relationship between the focal point of the mirror, 1 over f equals 1 over DO, the distance of the object, plus 1 over the distance of the image. So, but here we don't have what is the focal length, but we also know that the focal length equals half of the radius. The distance is of the half space from the radius. So which we can find equals negative 3.00 centimeters divided by 2. That equals negative 1.50 centimeters. Now that we know the values of focal length and the distance of the object, we can find the distance of the image by solving our equation for the mirrors. 1 over DI equals 1 over the focal length minus 1 over DO. Let's simplify this. That common denominator is f times DO, and we'll have a DO minus f. Now to find the DI, let's take the reciprocal from both sides. So we have DI equals f DO over DO minus f. Now let's plug in the numbers. Our object distance is 15 centimeters. I'm gonna make it 3 significant figures. 15 centimeters times, well, I was supposed to do the focal length first. I did the DO, and then let's do the focal length multiplied, negative 1.50 centimeters divided by DO is 15.0 centimeters minus negative 1.50 centimeters. So if you punch this into your calculator, you're going to get a negative 1.36 centimeters. So this would be the distance of the object image from the vertex of the mirror. Now, to find a magnification, let's see what we know about magnification. We know magnification equals negative DI over DO, which is the image distance over the object distance. So we will have negative, plug in the numbers, so negative 1.36 centimeters divided by 15.0 centimeters as the distance of the object, and that will give us positive 0.0909. So then I can completely say that the image is virtual and it's upright and it is reduced. So virtual, upright, and reduced. Now let's try to construct the image and make the graphical representation of that image. For that, let's start drawing our optical axis. Okay. And here I will put my spherical mirror. I'm gonna kind of continue with the dashed lines to approximate where exactly is the radius. So this is the center, and halfway from the center is the focal point. Okay, so now let's put our image approximately, well, if the radius is 3, then we have 18. That means it's 6 times the distance of the R, which I don't have enough space. So I'm going to put a little bit somewhere here, which is not to scale. So I'm going to call this an object. Now, let's make sure that we make this spherical mirror clear that this is a convex mirror, which means the shiny area is outside on the left side. And then to construct the image, we need at least 2 rays. I'm going to use the parallel ray, which is parallel to the optical axis. This is the ray is going to go hit the mirror and reflect by the law of reflection, and the reflected ray has to continue and meet at the focal point. And so let's call this parallel ray. The next one, I'm going to use the central ray, which has the direction of the center. It's going to be a little bit difficult for me to draw. So it's going to hit the mirror in a way that it just meets at the center. And then when it reflects, it's going to reflect back in the same direction. So this, where we have our 2 rays, non-real rays, continuations of the rays meet right here. This would be my image. So I'm going to call it image. As you can see, the image is virtual because it's made of the virtual rays. It is a little bit before the focal point, which is, it seems like I did a good job drawing it. So our distance of the image is negative 1.36 and the focal length is negative 1.50. So from here to the mirror, so this is 1.36 centimeters or meters. and the focal length was 1.5. So this is virtual because it's on the right side of the mirror. It is upright from our graphical representation, and it is reduced clearly. So it seems like our calculations and our drawing are in sync with each other. So thanks for watching, and stay tuned for more videos to come.